Albert Einstein. His name is almost synonymous with genius. The man who gave us the theory of relativity, who changed how we perceive space and time, who elevated physics into a form of art. And yet, even Albert Einstein missed something. A hole in reality, an absence that was subtle, elusive, but revolutionary. It was not discovered by force of theory or experiment, but by the quiet and piercing intellect of a German mathematician named Emmy Noether. In the shadow of Einstein's fame, Noether uncovered the symmetry behind the laws of nature, a deep structural order that even Einstein had not fully seen. This is a story not just about Albert Einstein's brilliance, but about the limits of that brilliance, and about the astonishing insight of Emmy Noether that revealed what Einstein had not predicted. What is symmetry? Symmetry is not merely a matter of visual balance, like the wings of a butterfly or the petals of a flower. In physics, symmetry is a principle of invariance. It means that something remains unchanged under a transformation. A law of nature is said to be symmetric if it holds true no matter where or when you apply it. For Albert Einstein, symmetry was central. His general theory of relativity was built on the elegant requirement that the laws of physics be the same for all observers, regardless of their velocity or location in space-time. But there was a deeper form of symmetry that Albert Einstein, for all his genius, did not fully grasp. That was the symmetry of action itself, hidden in the equations, but waiting to be revealed. And it would be Emmy Noether who would bring it to light. Emmy Noether and Einstein. Emmy Noether was a mathematician of rare depth. While Albert Einstein redefined gravity, Noether redefined the way we understand the laws themselves. Einstein admired her work. In a letter to David Hilbert, Einstein called Noether's theorem a piece of mathematical perfection. And yet she worked in obscurity, often barred from teaching because of her gender, and eventually driven out of Germany like Einstein. What Noether did was nothing less than revolutionary. She showed that every symmetry in a physical system corresponds to a conservation law. This was not merely elegant, it was structurally necessary. It was as if Noether had revealed the secret architecture behind the universe, and in doing so, exposed the piece missing from Einstein's own framework. General covariance. Albert Einstein's principle of general covariance was a cornerstone of general relativity. It demanded that the equations of physics retain their form under any coordinate transformation. In simpler terms, the laws must be indifferent to how we choose to measure them. This was Einstein's way of ensuring the universality of nature's rules. And yet, general covariance was a broad and formal symmetry. It lacked the specificity of what Emmy Noether would reveal. Where Einstein saw geometry, Noether saw logic, deep logical necessities that dictated conservation of energy, momentum, and charge. General covariance told us how to write laws. Noether's theorem told us why those laws conserve what they do. Einstein's vision was geometrical. Noether's was algebraic, and both were needed to truly understand the universe. The principle of least action. The principle of least action is one of the most profound ideas in physics. It states that the path a system takes is the one for which a particular quantity, the action, is minimized. Albert Einstein used variational principles like this in developing general relativity, but he never fully explored their connection to symmetry. Emmy Noether did. She saw that if a system's action is invariant under a continuous symmetry, then something must be conserved. This connection between symmetry and conservation is not just beautiful, it is foundational. Einstein, for all his insight, did not anticipate this deep relationship. It was the hole in reality he didn't predict, the idea that conservation laws are not axioms, but consequences of symmetry itself. Noether's first theorem. Noether's first theorem is a towering achievement in the history of science. It states that every differentiable symmetry of the action of a physical system corresponds to a conservation law. This means that if nothing changes when you shift time, energy is conserved. If nothing changes when you move in space, momentum is conserved. Einstein had intuited some of this, but he had not formalized it. Noether's theorem did more than complement Einstein's work. It revealed its underlying logic. Without Noether, conservation laws are observed facts. With Noether, they are necessary truths. And that changes everything. The continuity equation. The continuity equation is a mathematical expression of conservation. It tells us that if something is not being created or destroyed, it must be flowing from one place to another. In fluid dynamics, in electrodynamics, and in quantum mechanics, the continuity equation ensures that what goes in must come out. Emmy Noether's theorem provides the theoretical foundation for these equations. And while Albert Einstein worked extensively with energy-momentum tensors and field equations, he never saw the full implications that Noether's work had for the continuity of physical quantities. It was as if he had built the cathedral. But Noether discovered the hidden symmetry in its design. Escape from Germany. Both Albert Einstein and Emmy Noether were victims of political tyranny. Einstein left Germany in 1933 as the Nazi regime came to power. He went to Princeton, where he would live out his life in exile. Emmy Noether, less well known, but no less brilliant, also fled. She found refuge in America, but her time was short. She died in 1935, just 2 years after leaving Germany. The world lost her too soon, but her ideas endured. In the very institutions where Einstein continued his work, Noether's insights slowly began to take root. The physicists of the 20th century would come to see that while Einstein taught us how gravity warps space-time, Noether taught us how symmetry warps our understanding of reality itself. The third model, Higgs and quarks. The standard model of particle physics is sometimes called the third model, in contrast to Einstein's relativity and quantum mechanics. It describes the fundamental particles, quarks, leptons, bosons, and the forces that act between them. Central to this model is symmetry. Gauge symmetries determine the interactions, and spontaneous symmetry breaking gives rise to the Higgs mechanism. Here again, Emmy Noether's fingerprint is everywhere. Every force, every conserved charge, every interaction emerges from symmetry. Albert Einstein never accepted the standard model. He believed in a unified field theory, something more elegant, but the world of Higgs and quarks is built on the very symmetry principles that Noether uncovered. Without her theorem, there is no modern physics. The hole Einstein didn't predict had been filled, but not by him. Conclusion. Albert Einstein will always be a colossus in the history of science. His equations changed how we see the cosmos. But the structure behind those equations, the silent symmetry that ensures their consistency, was revealed by Emmy Noether. This was the hole in reality Einstein didn't predict, the idea that nature's laws are not just discovered, but required by symmetry. Noether's insight goes beyond Einstein, not in opposition, but in fulfillment. She did not just add to Einstein's work, she explained why it must be so. And that is the essence of philosophy, of science, of truth. Not just to describe the world, but to uncover the reasons it cannot be otherwise. This is the legacy of Emmy Noether. This is the brilliance of Albert Einstein. And this is the hidden architecture of reality, revealed not by force, but by symmetry.